Have you ever heard of mathematical sociology? It sounds like two words that have absolutely no business being together, right? But what if I told you it's the key to finding the hidden formulas, the secret code that drives our social world, everything from a weird game show puzzle to how an idea goes viral?
So, to get our heads around this, we have to start with a classic brain breaker, a puzzle that has been messing with people for decades, the Monty Hall problem. It's the perfect example of a glitch in our intuition, one of those moments where your gut feeling screams one thing and is completely, totally wrong.
Okay, I want you to really put yourself there. The studio lights are blinding, the audience is roaring your name, and in front of you are three perfectly identical doors. The choice is all yours.
And the stakes are high. Behind one of those doors is a brand new car. Behind the other two, well, they're goats. You're playing for the prize of a lifetime and trying very hard to avoid ending up with new livestock.
You take a deep breath, you point, and you pick a door. Let's say you go with door number 1. Right now, the math is simple. You've got a 1 in 3 chance that you pick the car. But here's the crucial part that everyone forgets. That also means there's a 2 in 3 chance the car is behind one of the other 2 doors.
But then, the host, who by the way knows exactly where the car is, walks over and does something very specific. He opens one of the doors you didn't pick, let's say door number 3, and reveals a goat. Now this isn't random. He deliberately showed you a door that was a loser. He just gave you a massive piece of new information.
So now there are only 2 doors left. Your original pick, door number 1, and the other one, door number 2. The host turns to you and asks the million-dollar question. Do you want to stick with your first choice, or do you want to switch? Now, what does your gut tell you? It feels like it's 50-50, right? 2 doors, 1 car. It has to be. But this is exactly where our intuition lets us down.
Believe it or not, the mathematically correct answer is you should always switch. I know, it feels totally wrong, but the reason isn't some kind of magic trick. It's just a quirk of probability that our brains are really, really bad at seeing.
To make this crystal clear, let's just blow up the problem. Forget 3 doors. Imagine 1,000 doors. You pick one. Then the host goes and opens 998 of the other doors, and behind every single one, he shows you a goat.
Okay, think about it. Your first pick had a tiny 1 in 1,000 shot of being right. That means there was a massive 999 out of 1,000 chance the prize was in that other group of doors. The host's big move was using his inside knowledge to clean up that huge group for you, leaving just 1 door left. That single door has basically absorbed all 999 of those chances. So, would you stick with your 1 in 1,000 shot or switch to the door that is almost certainly the winner? Yeah, you'd switch in a heartbeat.
And that is the exact same logic for our 3-door game. Your first pick had a 1/3 chance. The other 2 doors together had a 2/3 chance. The host just did you a favor by showing you which one of those 2 was the goat. So that entire 2/3 probability doesn't just disappear. It funnels onto the remaining door. Switching literally doubles your chance of winning the car.
And that feeling right there, that aha moment where a totally confusing social situation suddenly makes perfect sense with a little bit of math, that is the entire point of mathematical sociology. That game show wasn't just a puzzle, it was a mini social system. You had a host, a contestant, hidden information, and strategic choices all creating a result nobody would guess.
At its core, this is a field that's all about translating our messy, complicated ideas about society into the clear, precise language of math. And the goal isn't to turn people into numbers, not at all. It's to build these simplified models that can show us patterns and outcomes we'd never be able to see otherwise.
Seriously, you can think of it like putting on a pair of X-ray glasses for society. It lets you see past all the surface-level noise to the underlying structures and forces that are really running the show, just like it did with those game show doors.
Okay, so the game show puzzle is cool, but let's apply this to something from the real world. How about a really modern problem? How do opinions, ideas, and let's be real, misinformation spread through society? This is a classic job for a mathematical sociologist.
I just love this line from a research paper on the topic because it's so true, right? We're all constantly sharing our beliefs. But how do all those little individual conversations add up to create massive, sweeping social trends?
Well, the simplest model starts like this. You've got a population with a mix of opinions, say Team Red and Team Blue. Then you let people interact randomly, one-on-one. Every so often, someone gets persuaded and switches their opinion. If you let that simulation run, what often happens is that one opinion starts to snowball, until eventually the entire group reaches a consensus.
But of course, real life is way more complex. We don't just talk to random people. We have our social networks, our friends, our family, our followers online. The moment you add that structure into the model, the whole game changes. Now, an idea can't just jump to anyone. It has to spread along the connections that already exist.
And this is where it gets absolutely fascinating. You can run the model from the exact same starting point and get completely different outcomes. Sometimes red takes over, sometimes blue does, and sometimes neither one wins. Instead, you get these hardened clusters of opinion, little echo chambers, where the two sides stop talking to each other and society becomes fragmented. The very structure of the network can determine whether we end up in consensus or in conflict.
Now, these models of how opinions spread are just one example. This whole field is really a toolkit for exploring some of the biggest and most fundamental questions about how we all manage to live together.
For instance, it helped give us the Nobel Prize-winning idea of the strength of weak ties. The math shows that your best chance at finding new opportunities, like a new job, doesn't come from your best friends, it comes from your acquaintances. Why? Because your close friends are all in your bubble. They know what you know. Your weak ties are your bridges to totally new worlds of information.
It also helps us tackle that timeless struggle between cooperating for the good of the group and just looking out for yourself. It uses amazing concepts like the prisoner's dilemma, which is this tragic little model that shows why two completely rational people might end up betraying each other, even if it leads to a worse outcome for both of them.
And if you want to see this in action, just think of The Dark Knight. The Joker's ferry experiment is a perfect, terrifying example of the prisoner's dilemma. Each boat has to make a choice. Do we blow up the other boat in our own self-interest, or do we risk everything and trust them not to blow us up? It is pure, high-stakes game theory.
And that's really the big takeaway here. These models aren't meant to be perfect copies of reality. They're more like wind tunnels for social theories. You build a simplified world, you put an idea inside it, and you see what happens. And in the process, you uncover these deep, surprising truths about how our world works, like why you should always, always switch the door.
Which leaves us with a pretty profound final question. As these models get more and more sophisticated, what are the limits? We can model an idea going viral online, but could we one day use this to model the complex, chaotic spark that actually ignites a social movement, or even a revolution? We don't have the answer yet. The math is still being written.